So, hello everyone. I welcome you all to this next lecture of dynamics of machine. So far, we have studied about Watt governor. We have studied about Watt governor. We have studied about Porter governor and Powell governor. So, Watt governor was pendulum type governor. It was very simple in construction and operation. Okay, it had only fly balls. There was no central load or central weight attached to the spindle over the sleeve. Okay, and Porter governor and Powell governor, there was some dead weight added to the added over the sleeve. All right, for better control, and better sensitivity of the governor. All right. So these were dead weight type governor, that is Porter governor and Powell governor. Now we'll move forward to the spring loaded governor. Okay. In this, there are four types. We'll just quickly go through these four types: Hartnell, Hartung, Wilson Hartnell, and Pickering governor. So we'll be starting with the Hartnell governor. Okay. So this is what a Hartnell governor looks like. So as said in the previous slide, that it is spring loaded, right? So as you can see that the spring is mounted over this spindle. All right. And there is a nut in the spring with the help of which we can adjust its stiffness up to some extent. Also, there is a frame to cover the spring. Then there are fly balls. The fly balls are connected to the uh, sleeve with the help of bell crank lever. All right. And this is the sleeve, and the spring is mounted over the sleeve. So when the speed increases during rotation, when the speed increases, these balls will tend to move out because of centrifugal force. Okay. These balls will tend to move out. So it will acquire such position. Okay. So the spring would be pushing it downwards and the balls would be pushing it upwards. All right. So with the help of this, the speed is again, if the load increases, so the speed will decrease. So speed will decrease. Then what will happen? We have to alter the fuel supply accordingly. So this will operate the lever attached to the uh, fuel supply. All right, accordingly. Okay. So this was the typical diagram. Let's move to to understand properly. Let's move to the line diagram of Hartnell governor. Okay. So again, we have drawn one half of it, and over here it is the central axis. This is the sleeve. Okay, this red colored. This is the sleeve. All right. Then there is spring mounted over the sleeve, which has stiffness K. So this K is the stiffness of the spring. All right. And there would be the first position. So this is the lever. Okay. This is the lever. Let me draw it by another pen. This is the lever. And ball is mounted over here. The fly ball of mass small m is mounted over here. The sleeve itself will have some weight. So mg force will be acting. Again, frictional force will be acting. And this fs1 is the spring force. Okay. This fs is the spring force. All right. And how we'll calculate the spring force? It is stiffness multiplied by the deflection. Right. Delta L is the deflection and K is the stiffness of the spring. Okay. So we'll get the total spring force, what is acting on the spring. All right. Now, uh, this is the initial position. This when the this is B, and this is A. All right, this is the initial position. Mass is m1. Now, when the sleeve will move up, okay, when the sleeve is moving up, we'll get another position. We'll get another position, that is this will become B1. Okay, this is position number 1 when the sleeve is moving up. This is B1. So when this has moved like this arm will go something like this, right? Because this has moved up, so that means balls are moving outward. So the force which might be acting on the ball is F1 is equals to m r1 omega 1 square. Now what is r1? R1 is this distance. This distance is r1. All right, and this distance is a1. This vertical distance is a1. Okay, this vertical distance is a1. So the F1 force is m1 r1 omega square, or m r1 omega square, because the mass will remain same. This vertical distance is a1, and this horizontal distance is c1. Okay, from this position, this horizontal distance is c1. So when the sleeve is moving up, this is distance b1. This force is m r1 omega 1 square. This is distance a1, and this horizontal distance is c1. Okay, and the radius of rotation is r1. So these are the distances and forces corresponding to position 1 when the sleeve is moving up. Now consider when the sleeve will move down. When the sleeve will move down, what will happen? This will be the distance b2. Okay, this is the position of the sleeve. This is the position of the sleeve, and over here the other end of the ball will move something like this. Okay, so the radius of rotation is r2. Radius of rotation is r2. This horizontal distance is c2 from the mean position. This vertical distance is a2. Okay, this vertical distance is a2. All right, and the force which is acting is, as you can see over here, the force which is acting is F2. Okay, the force which is acting is F2. All right, and the lift of the sleeve will be from lower position to the upper position. Okay, from this position when this distance is b2 to next position when this distance is b1. All right, so this is how it will be operating, and we'll be doing all our calculations with respect to this instantaneous center, that is I. Okay, this hinge point. All right, we'll be doing our calculations according to this. Okay, so this kind of lever is called as bell crank lever, which is hinged at one point, and both the two arms are moving accordingly. Okay, now let's move forward. I hope the diagram is clear. So we'll get to see this kind of formation happening, right? So this total distance is r1 minus r2, and the vertical height of this triangle would be a. The uh, the horizontal height of this triangle would be this b. Okay, and this lift would be proportional to this distance, that is r1 minus r2. All right, if you watch it over here clearly, so this triangle, okay, and this triangle. So the extreme positions are taken, and accordingly it is drawn. Okay, so we have this distance, this I'm marking with pink color, right? So this distance, that is the base of this triangle, it is r1 minus r2, right? and the distance R1 minus R2 would be proportional to the lift of the sleeve. Okay, so if we want to determine the lift, we can uh, find it in the proportional manner. So F1 is m R1 omega 1 square, F2 is m R2 omega 2 square, right? Because R is changing and omega is changing. So these are centrifugal forces. Then spring forces would be Fs1 is equals to K into final compression, and Fs2 would be is equals to K into initial compression. So it will be proportional to this distance. All right. The net spring force would be Fs1 minus Fs2. So Fs1 minus Fs2 is equals to K into net compression in the spring. And what is the net compression? That is the lift. The net compression is equals to the lift of the spring. All right. So, and lift would be proportional to, see from here, this lift divided by this. According to similar triangle properties, the lift, that is this distance, divided by the its central distance B, is equals to R1 minus R2 divided by this central distance A. Okay, so the lift becomes R1 minus R2 into B by A. So we have substituted lift is equals to R1 minus R2 into B by A. So the spring force, difference in spring force, is equals to K multiplied by R1 minus R2 into B by A. Okay, so we can use this expression, these forces. Now we'll take moment about this point I. Okay, taking moment about this point I. So what are the forces? Let's first see what are the forces. One force is this centrifugal force. Another force is this weight force of the ball. Okay, and the third force is this, the weight of the sleeve, the friction force, and the spring force. Okay, so this F1 force and uh, this mg force, while in position 1, will try to rotate this entire system in clockwise direction about this hinge point. All right, so these are on the same side, and this is currently, this is with the plus sign. That is F1 into A1. F1, this is the line of action, and what is the perpendicular distance? It is equals to A1. Okay, and then we have mg. Mg force is here. This is the line of action, and what is the perpendicular distance? Its distance is C1, right? C1 over here. So this C1. Then this force, the direction of force is something like this, and its perpendicular distance is B1, right? For the first position. And similarly, we can write the second equation when the position of the ball is over here and it is over here. Okay. So these are the two governing equations. Now, if we take some assumptions, the first assumption is neglect the obligative effect. So what is obligative effect? If A1 is equals to A2 is equals to A, that is all these vertical distances are same, right? If all these vertical distances are same, it's is equals to A, and the horizontal distances, that is B1 is equals to B2 is equals to B. Okay. So these are taken as equal, and the ball gravity is negligible. So mg is equals to 0. Okay. Why mg is equals to 0? Because m cannot be equals to 0. Mass cannot be equals to 0. So these equations will uh, get reduced to F1 is equals to A is equals to mg plus F, that is friction force, plus Fs1 spring force multiplied by B, and this F2 into A is equals to mg plus F plus Fs2 by 2 into B. All right. So these are equation number 3 and 4. These are equation number 1 and 2. So these are the equations which we are going to use. Now we'll subtract these two equations and we'll get spring force. The difference in spring force is equals to 2 into F1 minus F2. Okay. Divided by A by B, multiplied by A by B. This F1 and F2 are the centrifugal forces at different positions. All right. So this is what we are going to use while uh, studying the Hartnell governor. Now let's go through its numerical. In a Hartnell type governor, the extreme radii of rotation of balls are 80 mm and 120 mm respectively. Sorry, 80 mm and 120 mm. So R1 and R2 is given to us. The ball arm and sleeve arm of the bell crank lever are equal in length. The ball arm and the sleeve arm. So this one is the ball arm. This A is the ball arm and sleeve arm is this B. So both are equal in length. So A is equals to B. All right. The mass of each ball is 2 kg and the speed at extreme positions are 400 rpm and 420 rpm. So minimum and maximum speeds are given and the mass of ball is given. Find the initial compression and of central spring and spring constant. Neglect the sleeve mass. So capital M is 0 and initial compression and final compression. Find the initial compression. Okay, and spring constant is to be determined. So B is equals to A. We'll get lift is equals to R1 minus R2 into B by A. So B by A, this will be 1. So lift will be equals to R1 minus R2. Okay, R1 and R2 is given to us as 120 and 80. So lift comes out to be 40 mm. Okay, now with the help of lift, we can move forward. This small m is 2 kg, mass of balls. N2, that is the lower speed, is 400 rpm, and higher speed, maximum speed N1 is 420 rpm. All right. So omega 2 and omega 1 can be determined. So F1, F2 would come out to be 464.266 Newton and 280.737 Newton. All right. So this Fs1 minus Fs2, that is difference in spring force, would be equals to 2F1 minus F2 into B by A. Since B and A are equal, so this ratio becomes 1. So difference in spring force comes out to be 367.058. Okay. And this difference in spring force is equals to stiffness multiplied by lift. So we determine the value of lift as 40 mm. So this spring constant comes out to be 9.176 Newton per mm. Okay. Or kilonewton per meter. Okay. So initial compression was initial compression. This Fs2 would be equals to K into initial compression. So there are two unknowns. So we'll use this equation that F2 is equals to mg plus F plus Fs2 by 2. So M is equivalent to 0. Friction force is not given to us. So this A and B are equal. So they will get cancelled. So Fs2 comes out to be 561.472 Newton. So initial compression would be Fs2 divided by K. This would be equals to 61.189 mm. All right. So I hope this is clear to you, Hartnell governor, and how we'll approach the numerical for this Hartnell governor. Okay. So I'll conclude this class today over here. Thank you, everyone.